Hassler here. I'm going to go ahead and give you notes on 13.2. We're still graphing systems of equations, but we're going to look at some different aspects of graphing those systems of equations. Before we do that, we're going to determine if an ordered pair is a solution to a given system. And we kind of talked about this yesterday, but this is a more formal check. Okay, so to be a solution, the ordered pair must make both equations true. Okay, if the ordered pair makes only one of the equations true, the ordered pair would not be a solution to the system. Remember, what I'm really trying to identify is if the two graphs intersect at that point. In other words, do the two functions have this point in common? Okay. So in order to make that determination, I'm going to do problem 1. In order to make that determination, I am going to start by substituting -6, -2 into the first equation. Now remember, -6 is the x, -2 is the y, and so I'm going to replace, in this equation, I'm going to replace the y with -2 minus, I'm going to replace the x with -6 equals 4. So I'm just rewriting the equation. -2 minus the x, which is -6, and that equals 4. This is really -2 plus 6, and -2 plus 6 is 4. And so I get a true statement. And what that means is that if I were to graph this equation, this point, hello, there we go. This point would be a point that is on this line, okay? Because when I substituted that point in, I got a true statement. All right, I want to check if the other equation makes a true statement. Okay, just have to leave that there. And in order to do that, I'm going to check the second equation. I'll do that here in blue. So again, I'm going to rewrite the second equation, -2 equals -1/3. I'm replacing the x with -6 plus 4/3. So -2 equals, well, -1/3 times -6 is a +2 plus 4/3. Those two things are not going to equal each other, right? 2 plus 4/3 is the same as saying 3.3 repeating. Those two things are not equal. And so because those two things are not equal, this ordered pair is not a solution because the second statement ended up being false. What that means is that this point is not on the second line. If it's not on the second line, then certainly the two equations cannot intersect each other at that point. These two equations do not have the point -6, -2 in common. Your job will be to do problems 2 and 3. Let's move on. If I'm given a table and I'm asked to determine the solution or solutions to the system of equations, how would I go about doing that? Well, the solution, remember, is a point that both functions have in common. So if both functions have these points in common, I'm going to check for same y values. I'll do the first one with you. All right. So I didn't actually tell you what the two equations were, but here's what I know. I know that for y1, my output is in this column here, and that goes with any of the inputs in the x column. I also know that I have this y2 graph, and the outputs for y2 are in this column, and they also correspond to those x values. Those x values relate to both functions. In other words, in one of the functions, I have the ordered pair, -5, 16, and that would be related to y1, versus in the other function, I have the ordered pair -5, -12.5. So I use that x value for both functions. If I'm looking to see where both functions have a point in common, then I'm looking for where they have the same y value. So as I start to scroll down my table, I notice that I have a common y value when x is -3. I also notice as I look down my table that that's the only place where that happens. And what that means is that -3, -12 is a point on both graphs. If it's a common point on both graphs, they intersect at that point, and that point would be my solution. Your job would be to do problem 5. The last thing that we're going to talk about is using our calculator features. Again, we talked a little bit about this yesterday in class, but we're going to review some window ideas. So using your graphing calculator to find the solution means that I might have to adjust my window if I can't see all points of intersection, and I might have to isolate y first in order to put this function into y equals. So let's take a look at problem 6. I would substitute the first function into y1 and the second function into y2. The problem is that this first function is not isolated for y. I have to get this y by itself in order to type it into y1. So I would have to subtract 2x on both sides. So that I would get y equals 8 minus 2x. Hey, that's the same as saying y equals -2x plus 8. So either way, in order to type this into my equation, I have to have the y isolated. I'm going to go to my graphing calculator, do this with me. And I'm going to go to y equals, and I'm going to type that first function in, 8 minus 2x. I'm going to hit enter. And in my second equation, I'm going to type in 5 divided by 2x plus 26. Now, just to make sure that my window is set the way that I'm used to seeing it, I'm going to hit zoom 6 to get back to that normal viewing window. And I see that I have these two lines, but I can't see where they intersect. So I'm going to have to change my window. They're going to intersect in the upper portion of my graph, and so I need to change the y max in order to see. I go to window. I'm going to arrow down to y max, and I'm just going to pick a number to try. I'm going to start with 20. I'm changing the y max to 20 in hopes that I can now see the intersection point. And I can. And now I'm going to go through and I'm going to make my calculator find this intersection point by hitting second, trace, option number 5. Because there's only one intersection point, I don't have to move my cursor closer to the intersection point. I can just hit enter 1, 2, 3 times. And it tells me that my intersection point occurs at -416. That point, -416, is on both of those lines, and that's where those two lines intersect. Those two lines have the point -416 in common. Your job is going to be to do 7 and 8. All right, let us know if you have any questions.